Hello everyone, let us begin the enrichment class along with the regular schedule. So since it is the very first class, so I have decided to start with the topic that we have been discussing in the previous class. Remember, the syllabus remains the same for the enrichment classes, means for the JEE mains and for the NEET exams as of now. So let us discuss something which will be important to class 11, class 12, means for this competitive exams, this topic is immensely important, and since we have been discussing already, it will be easier for you people as well. We will discuss general organic chemistry, the common things which you already know. So let us directly go into the problems because the basics are already known. So today's topic will be the stability of carbocation and carbanion. Yes, I know we have been discussing the problems of it already, but since we are just getting used to it, let us start with this topic. So let us begin with the first question for today. The question is, which one is the most unstable carbocation among the following? And here are the questions. Now you see this, among these four options, let us understand unstable carbocation. That means the positivity of the carbon has to be neutralized. Now let us see among this, in which case it will be the best. Let's see. So let us take the first option, which is the option A. Here what happens, like CH3 bond CH2, and here is the plus charge. So of course CH3 group is having the plus I effect. So with the help of this plus I effect, what it can do? It can push the electrons towards this plus charge. In option B also, see there is Cl, CH2, CH2 plus. The Cl group is having the minus I effect, right? So with the help of minus I effect, obviously the electrons are going to go towards this side. That means from this bond also electrons are basically shifting towards the other side, making this one little bit unstable for sure. Little bit. See the third option, option C, CH2 plus, then C double bond O and H. So here if we see, obviously between carbon and oxygen the electronegativity difference is huge. So delta minus and delta plus already. See, the two carbon adjacent to each other. This carbon by no means are going to have the negativity or the negative charges. That means between these two similar charges will come, making this region hugely unstable. So the carbonyl group over here making the region exceptionally unstable. Let us see the fourth option, CH2, O, CH3, and here is the plus charge. See carefully, there are these two electrons. So it will have the lone pairs, right? According to the Lewis dot structure, this can come over here, neutralizing the plus charge. So here, this one is comparatively stable. So among all this, if I had to choose one, which one is the most unstable, my answer will be this one because of this region. So that's the answer. The next question for today is the most stable carbocation. The most stable carbocation among these four. Carefully see the questions. So all of these are cyclic structures. So if we have to compare the stability among them, let us see the first case. Here you see, first of all, these two are having the double bonds within the cyclic structures. So obviously the chances of getting resonance stability is more. So basically the comparison will be in between these two, because the last two, in these two cases, of course, the cyclic groups means CH2, CH2, CH2 like that. So these groups are having the plus I effects here also. But here the double bonds are present, so the effectivity will be much more. Let us see one by one. In the first case, here, check carefully. If I shift the double bond towards the plus charge, what happens in the next is that the double bond will go here, the plus charge will be here, then there will be double bond. Similarly, in the next step, this can come here. So it will be like double bond is here, double bond is here, and the plus charge is here. Now again, if I shift over here, the plus charge will come here, and accordingly. But here you see, it is 1, 2, 3, 4, 5, 6, 7. So if the double bond rotates, it forms something like this. Just a minute. So double bond is here, plus charge is here, double bond, and in the next step, the double bond can rotate once again. So double bond will be here, double bond was already here, then there is a plus charge. Again, now double bond will be here, plus charge, double bond again. So as I could see over here in the second case, clearly if you want to draw, the more number of resonating structures will be formed. So double bond is here, double bond is here, double bond is here, and the plus charge is here. So more number of resonating structures over here. In this case, as I have said earlier, the comparison is basically between these two. More number of resonating structures, hence more stability to this carbocation. So according to me, this will be the correct option. These two are also a little bit stabilized, but comparison was between these two mainly, and out of these two, this one will get the upper hand in terms of stability. Third question for today is similar, is the most stable carbocation among the four. Let us see the four options carefully. So here, in the first case, you see the position of the carbocation. You see, on both sides there are bonds and there are groups, substituents. So there will be plus I effect from both the sides, and obviously this is a bigger group, will be having better plus I effect. So it's a 2-degree carbocation. Here if we see, it is absolutely at the terminal position. So the plus I effects can come only from this sides. So it's a primary carbocation. In this case, see the position of the carbocation. There are 3 bonds on the 3 sides. All of these are substituents. This one. So the plus I effects will be from all the 3 sides, making it a 3-degree carbocation. And over here also, although the substituent is different compared to the previous one, but this is also a penultimate position. So it is a primary carbocation, and the plus I effects obviously is only from one side because there are 2 hydrogens only over here. So out of these 4, if we have to compare the stability, obviously the plus charge onto this carbon will be stabilized from all the 3 sides over here. It is a 3-degree carbocation, and hence it is the most stable one. So the correct answer will be the option C. The next one is also a similar question. Here we had supposed to discuss the correct order of stability, but the systems are changed. There are 2 aromatic systems, 3 aromatic systems rather, and one this one. So we have to compare. Now let us see the groups which are attached. One is CH3 group, one is OCH3 group, and there is no group which is attached, only this CH2 plus which is common in every case, and here it is the alkyl group. Now if we have to compare the stability, as we all know, the aromatic system provides more stability simply due to resonance. So comparison will be between the 3, although this can provide stability due to plus I effect. Now let us check one by one. Let us check this one first. Which effect is here? So CH2 plus, what it can do is, it can provide stability by the means of resonance. Sorry, it will be plus over here, double bond, double bond. Then it can go here. So it will be like double bond, plus charge, double bond, CH2. Then it can come here. It will be like plus charge, double bond, double bond, double bond, CH2. What I mean to say is, this aromatic system provides stability to the plus charge by means of resonance. Now, with the help of this discussion only, we can see what are the further attachments. One is OCH3 group, one is CH3 group. We know that CH3 group provides plus I effect to the ring. So the point is, if the electrons are being circulated in the ring itself, so the ability of the ring electrons to go towards the positive charge will be even more. I would like to say once again is that CH3 group pushes the electron by the means of plus I effect towards the ring. Now there will be an excess of electron in the ring, so it will be the common tendency of the ring electrons to go towards the positive charge. The things will be getting easier. So if there is a plus I effect, it increases the electron circulation within the ring. Further, it helps in providing stability to the plus charge. Now, if we see this one, that means over here CH2 plus and O CH3. The oxygen will have the lone pair, and these lone pairs can be given so easily the electrons can circulate. This tendency, this is, we can say, it is the plus M effect or plus R effect, you can say. It is the resonance stabilization. So this plus R effect, with the help of this plus R effect, the electrons are being donated, which is much greater than this plus I effect. We know that plus R will be having greater capability than plus I. So what we can say is, due to the plus R effect over here, the stabilization of the carbocation will be greater. So the most stable out of the lot, if I write down the order over here, the B will be most stabilized, followed by A, followed by C, then D. This is the correct order. Then let us talk about the carbonyls. Here the question that is given is, in which case the first one is more stable than the second one. So here you could see, first one has to be more stable than the second one. So if we see the options, here you see the first one, C, Cl, Cl and Cl. 3 chlorine groups are attached, and here 3 fluorines are attached. We all know that the chlorines can drag the electrons, fluorines can also do the same. The capability of fluorine in this case is greater, so the negative charge will be dragged away by these 3 fluorines over here in a much better condition, in a much better way. So here the second carbanion will be more stable. If we see the option C, here also the negative charge will be easily delocalized, and in the third case also, if we see that the 3 CH3 groups are attached to a carbon which is negatively charged, that means 3 of them will donate the plus I, means the electrons will go, and here there is only one CH3 group adjacent to the CH2 minus, that means only one plus I effect. So here obviously it will not be more stable, this one will be more stable, because more the negative charges will be going towards this carbon, the electron density over here will be more and the stability will be less. Here also, due to the delocalization of the negative charges, this will be more stable. But if you see the option B, between these two, sp hybridized and sp2 hybridized, negative charge is on carbon. Carbon is sp hybridized. Hybridization is sp, and here the negative charge is on carbon, which is sp2 hybridized. We know between S and P, the S is having in sp the 50% S character is there, and in sp2, which is 1 by 3 into 100, that is 33.3% S character. Again, I would like to repeat this sentence, that in sp, since it is 50% S and 50% P, and here it is 33.3% S, and rest of the percent is P. And the greater will be the S character, more will be the stability, because the electrons would like to be comfortable in the S orbitals compared to the P orbital, since it is more closer to the nucleus. So only in this case we should say that the first one will be more stable than the second one, because of the higher percentage of S character, which is more closer to the electrons, nucleus, and the electrons are more comfortable over there. But in rest of the cases, the second one will be the more stable one. So as per the given question, first one, in which case is the more stable one? The answer is option B. The next question for today is the decreasing order of stability between this A, B, C and D. So it is in all the cases, one thing is common, is the CH2 minus on the top of a ring. So we are comparing the stability of the carbanions. Let us see these three. All of these are substituted aromatic compounds, where along with CH2 minus, one more group is present. What are the capabilities of these groups? CH3 plus I effect. NO2 withdraws the electron, so it is having minus R effect because it withdraws the electron by means of resonance. OCH3 obviously is having plus R effect, as we have seen one problem regarding that previously. So if we see this one here, compared to others, there is no such effect. Obviously ring is having its own capability, but other than that, there are no such extra groups present. So we all know that in the ring, if the electron goes, so the stability will be decreased. So what happens is, the first one, NO2, which withdraws the electron from the ring, if it withdraws the electron from the ring, it will have the chance, the ring will have the chance to further drag the electron from the CH2 minus. That means more is the capability of withdrawal by this group, more will be the electron deficiency within the ring, and further the ring will have the capability to take this negative charge within it to further stabilize the product. So here this one, C, will be the most stable one. Then these two, in both the cases, the electrons are going to be pushed inside the ring. So the ring will be electron rich, and the tendency to neutralize or to stabilize the negative charge will be less, because the ring itself is further electron enriched by then. Here there is no such case. So after C, A will be more stable, followed by these two. Out of these two, here the capability of pushing the electrons within the ring will be more. Ring will be further electron rich compound. So the negative charge will be comparatively less stabilized. So this one will be little bit better in terms of stability. So option B, then option D. This will be the correct order.